Good morning, everyone. Today, I will take you on a journey to explore a fascinating and mysterious topic: the fundamental role of mathematics in astronomy. First, what is astronomy and what is mathematics? Astronomy studies everything in the universe beyond Earth's atmosphere, and mathematics is the key to unlocking its secret. From planetary motion to black hole collisions, from galactic evolution to measuring stars light years away, mathematics is everywhere. Not only that, we can use algebra to express relationship between variables such as the Kepler's law of planetary motion, which describe how planets orbit the sun. Second, we can use calculus. Calculus is essential for understanding motion and change in celestial mechanics, and used in Einstein's general relativity to describe how gravity affects the space-time. Third is the statistic. Statistic is used to analyzing the large data set from telescopes. The fourth is the trigonometry. Trigonometry is used to in the parallel method where angles and distance are measured to determine how far away a star is. Not only that, we also can use logarithm to in the magnitude scale where the brightness of stars is measured using a logarithmic function. So today I will discuss four mathematical applications in astronomy. The first is the Newton's law of motion and gravitation. The second is Kepler's law. The third is astrophotometry, and the fourth is the parallax. Newton's law of universal gravitation states that gravitational force decreases with distance and mass. It also describes the relationship between forces acting on a body and its motion due to these forces. Newton's law of gravitation states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So we will use out the equation F is gravitational force is equal to gravitational constant time with masses of two objects and divided to square of the distance between the objects. So as the distance r is increased, the force will decrease exponentially by the square of the distance. This is why planets farther from the sun experience weaker gravitational attraction. The second is the Kepler's law. Kepler's law of planetary motion describes how planets orbit the sun. Kepler's first law is law of ellipse. Law of ellipse states that the planets move in the elliptical orbits with the sun at one focus. It means that their distance from the sun changes throughout their orbit. Kepler's second law is law of areas. Law of area explains that a line joining a planet and the sun sweep out equal areas in equal times interval. It will cause the planets to move faster when closer to the sun and slower when farther due to angular momentum conservation. And the Kepler's third law is the law of period. Law of period states that the square of the planet's orbital period is directly proportional to the cube of its semi-major axis. It means that the planets farther from the sun take longer to complete an orbit. This law helps the astronomers to predict the planetary motion and are fundamental in celestial mechanics. Kepler's first law states the planets move in the elliptical orbits with the sun at one focus. The equation of an ellipse in condensation is x squared over a plus y squared over b is equal to 1, where the a is the semi-major axis and the b is the semi-minor axis. The focus distance from the center is given by c squared is equal to a squared minus b squared. The sun is located at plus minus c 0 along the major axis. If the c is equal to 0, the orbit is circular. Otherwise, a larger c indicates a more elongated ellipse. For example, if a is equal to 10 AU, and b is equal to 8 AU, then c is equal to square root 10 square minus a square is equal to 6 AU. It means that the sun is positioned 6 AU away from the center. Kepler's second law are known as the law of areas, state that a planet does not move at a constant speed along its orbit, but instead moves faster when closer to the sun and slower when farther away from the sun. It's because the line joining the sun and the planet sweeps out equal areas in equal time intervals. It means that as the planet approaches the perihelion, which is the closer point to the sun, its gravitational pull increases and cause it to accelerate, while at the aphelion, which is fastest point from the sun, the weaker gravitational pull causes it to decelerate. This variation in speed is a result of a conservation of angular momentum, ensuring that orbital motion balance gravitational forces. Kepler's third law are known as the law of periods, state that the square of a planet's orbital period is directly proportional to the cube of its semi-major axis. The formula to determine the orbital period is given by t squared is equal to 4 pi square r cube divided to gm, where the t is the orbital period, the r is the semi-major axis or orbital radius for circular orbits. The m is the mass of the central body, like for example the sun, and the g is the gravitational constant. This law implies that the planets farther from the sun take longer time to complete an orbit since the orbital period increases with distance. It is fundamental in celestial mechanics and helps in calculating the motion of planets, moons, and even exoplanets. Astrophotometry is a technique in astronomy used to measure the flux or intensity of light emitted by celestial objects. This is done using the telescopes equipped with photometries, such as CCD photometries or photoelectric photometries, which convert the light into electric current through the photoelectric effect. So in this field, we will use both formulas, distance modulus and inverse square law of light. The distance modulus formula is used in astronomy to determine the brightness and distance of celestial objects by applying the magnitude system, which follow a logarithmic scale. The formula is given as small m minus 2 big M is equal to 5 log d base 10 minus 5, where the m is the apparent magnitude, is that how bright the object appears from Earth. The big M is the absolute magnitude, where the intrinsic brightness of the object at a standard distance of 10 passes, and D is the distance to the star in passes. This equation helps astronomers to classify the stars based on their luminosity and distance, allowing from allowing for a better understanding of stellar properties and the structure of galaxy. The inverse square law states that the observed intensity of a physical quantity decreases proportionally to the square of the distance from its source. In astronomy, this law applies to the measurement of a star's brightness, given by the formula F is equal to L over 4 pi d square, where the F is the observed flux or the brightness as seen from the Earth. The L is the luminosity, which is the total energy output of the star, and D is the distance to the star. This means that if the distance to the star doubles, its observed brightness becomes 1/4 of its original value, and if the distance triples, the brightness drops to 1/9. This principle is crucial in determining stellar distance, luminosities, and the overall structure of the universe. The inverse square law explains how the intensity of light or any radiating energy decreases with distance from the source. If S represents the light source and R represents the measure points, the flux lines spreading outward illustrate how energy distributes over an increasing area. Since light radiates in all directions, the total number of flux lines remain constant regardless of distance, but their intensity, which is lines per unit area, decreases. This happens because the surface area of a sphere surrounding the source increases with the square of the radius 4 pi r squared. It means that the same energy is spread over a larger area. Mathematically, the flux at a given distance follows the formula for F is inversely proportional to the r square. Meanings that if the distance doubles, the flux become one quarter of its original value, and if the distance triples, the flux is 1/9. This principle is fundamental in astronomy for understanding the stellar brightness, gravitational force, and the electromagnetic radiation, since it governs how the light and energy diminish across vast cosmic distance. Parallax is in astronomy refers to the apparent shift in the position of a celestial object when observed from two different vantage points. This effect occurs because the objects closer to the observer appear to shift more than those farther away. Geocentric parallax measures this shift using 2 points on Earth, while the heliocentric parallax measures it from opposite sides of Earth's orbit around the Sun. The trigonometry is essential in determining the celestial distance through the parallax measurement, which rely on the apparent shift of a star against the background when viewed from different positions in Earth's orbit. The distance to the star d is in parsecs is calculated using the formula d is equal to 1 over p, where the p is the parallax angle in arc seconds. In one parsec equals to Since one parsec equals to 3.26 light years, a star with a parallax angle of 1 arcsecond is exactly one parsec away. The smaller the parallax angle, the farther the star. This method is a fundamental tool for measuring distances to nearby stars and serves as the basis for the cosmic distance ladder in astronomy. So now, here is a question: how the mathematics as a tool for real-world astronomical application. Orbital mechanics is essential for designing spacecraft trajectories, ensuring the precise navigation and efficient space travel. Missions like the Perseverance rover on 2020 rely on orbital equations to accurately reach the Mars. It used the principles such as the Kepler's laws, Newton's laws of motion, and also gravity assist maneuvers to optimize the journey. The mathematical modeling helps astronomers to predict the gravitational influences from celestial body, calculate the field-efficient transfer orbits, and also account for the factors like atmospheric drag, thrust vectoring, and orbital correction. One of the key concepts is the whole mass transfer orbit, which minimizes the fuel consumption when moving between two planetary orbits. Additionally, advanced techniques like Pastel coordinates and N-body simulation allow for precise interplanetary navigation. Without these complex calculations, spacecraft would struggle to maintain course, dock with dock with stations, or land on distant worlds. Orbital mechan- Orbital mechanics remains a cornerstone of modern space exploration. enabling humanity to explore the moons, planets, and beyond with increasing the precision. High performance computing is revolutionizing astronomy by enabling the efficient processing of vast celestial datasets. Advanced computational frameworks such as the MapReduce and machine learning algorithms significantly accelerate the data analysis, with studies with the studies showing a 24 increase in galaxy image processing speeds. These powerful systems are crucial for handling the data from large-scale surveys like the James Webb Space Telescope and the interferometers such as the Square Kilometre Array. HPC allow the astronomers to model cosmic structure, simulate the galaxy formation, and analyze the exoplanet atmospheres with unprecedented precision. Techniques like parallel processing, cloud computing, and GPU acceleration further enhance the efficiency, making it possible to process petabytes of astronomical data in real time. As telescope resolutions improve and data volumes continue to grow, HPC remains a cornerstone of modern astronomy, facilitating the discoveries about the universe that would be impossible with traditional computing methods. Statistical methods are essential in astronomical data analysis, helping astronomers interpret the vast dataset from telescopes and space observatories. Large-scale surveys such as those conducted by the Hubble Space Telescope, Gaia, and the Sloan Digital Sky Survey generate the massive amounts of data that require the probabilistic models to detect meaningful patterns and trends. Techniques like the Bayesian inference, machine learning classification, and Monte Carlo simulation helps filter the noise, quantify the uncertainties, and improve the accuracy of cosmic discoveries. Hypothesis testing and regression analysis allow the astronomers to identify the correlations between celestial phenomena such as the relationship between a galaxy's redshift and its distance. Additionally, statistical outlier detection is crucial for distinguishing the real exoplanet signals from instrumental noise in transit photometry. Without rigorous statistical analysis, separating actual celestial objects from observational errors would be extremely challenging. These methods form the foundation of modern astrophysics, cosmology, and exoplanet research, ensuring that scientific conclusions drawn from astronomical observation are robust, reliable, and also data-driven. Machine learning has revolutionized the astronomy by enabling the rapid detection and classification of its celestial bodies. Convolutional neural networks has demonstrated remarkable accuracy in identifying the multi-planet system, achieving 96% accuracy. These, these AI-driven models analyze the vast telescope dataset far more efficiently than human researchers, allowing for the discovery of new exoplanets, black holes, and also the supernovae. Supervised learning techniques such as random forests and enhanced exoplanet candidate verification by distinguishing real signal from instrumental noise. Additionally, unsupervised learning methods like the clus- clustering algorithm helps classify galleries, variable stars, and transient cosmic events. Machine learning also plays a crucial role in gravitational wave detection as deep learning models shift through data from observatories like LIGO and Virgo to identify the wave patterns from colliding black holes and neutron stars. As the volume of astronomical data continues to grow, machine learning driven tools are becoming indispensable for accelerating the discoveries, improving the classification accuracy, and uncovering hidden patterns in the universe. Mathematics is the backbone of modern astronomy, transforming raw observational data into scientific insight about the universe. Mathematic models allow scientists to interpret complex cosmic phenomena behavior of from the behavior of the black holes to the elusive nature of dark matter. Advanced algorithms process vast amounts of telescope data, re- revealing hidden tra- uh, revealing hidden patterns in galaxy formations, stars, clusters, and cosmic microwave background radiation. Predictive modeling enables astronomers to forecast celestial events with high precision, such as the planetary transits, supernova explosions, and asteroid tra- trajectories. Statistical techniques Statistical technique, machine learning, and computational simulation refine these predictions, reducing uncertainties and improving accuracy. Without mathematical tools like differential equation, probability theory, and Fourier analysis, astronomy will struggle to extract meaningful conclusions from raw data. These mathematical frameworks empower scientists to decode the universe mysteries, leading a groundbreaking discoveries that reshape our understanding of space and time. So now I will introduce about the fundamental role of mathematics in astronomy. Mathematics serves as the fundamental framework for astronomy, providing a structured approach to quantifying, modeling, and predicting cosmic events. The laws governing celestial bodies, including the Newton's law of motion, Kepler's law of planetary motion, and Einstein's theory of general relativity, are deeply rooted in mathematical equations. These equations allow the scientists to simulate the interactions of massive objects, predict the planetary object, and understand the gravitational effects on the galaxies and black holes. Techniques such as the tensor calculus help describe the curvature of spacetime, while the differential equations model the evolution of stars and galaxies over time. Computational simulations based on these mathematical principles have enabled precise predictions of gravitational wave, black holes merger, and cosmic expansion. Without mathematics, the fundamental principle of astrophysics will remain purely theoretical, lacking the precise validation needed to confirm our understanding of the universe. Through the mathematical analysis, astronomers can decode the cosmic mysteries, verify theoretical prediction, and uncover the new frontier in space exploration. Numerical relativity is a powerful computational approach that helps scientists understand how gravity wrap the space-time and influences massive celestial events. By solving Einstein's field equations using advanced numerical methods, researchers can simulate extreme astrophysical phenomena such as merging black holes, neutron star collisions, and gravitational wave propagation. The Bulger and Shapiro demonstrated that the numerical relativity simulations provide the computational solutions for these high-energy cosmic events, offering insights that would be impossible to obtain through direct observation alone. These simulations are essential for studying gravitational waves, which which were first detected by LIGO in 2015, confirming a key prediction and general relativity. By, incorp- by incorporating techniques like finite difference method, spectral method, and additive mesh refinement, scientists can create precise models of spacetime distortion, shedding light on black hole dynamics, relativity, relativity, jet formation, and the structure of spacetime near the singularities. The ability to model these high-energy astrophysical events relies entirely on advanced mathematical equation and computational power, making numerical relativity a cornerstone of modern theoretical and observational astrophysics. Newtonian mechanics and orbital calculus continue to be fundamental in modeling galactic evolution and large-scale astrophysical structures. Despite advancement in general relativity and quantum mechanics, classical Newtonian equations provide essential approximation for understanding planetary orbit, stellar motion, and galactic dynamics. Binney and Tremayne illustrate how these frameworks bridge the gap between traditional physics and modern astrophysical application, enabling astronomers to calculate the gravitational interactions, determine the stability of star system, and also predict the motion of celestial body with high accuracy. Newton's law of universal gravitation explains how massive objects attract each other, while Kepler's law, derived from Newtonian mechanics, describe planetary motion around the stars. Additionally, Newtonian models are crucial for studying dark matter by analyzing the unexpected rotational curves of galaxies, which suggests unseen gravitational influences. Even in the era of relativistic physics, Newtonian mechanics remains indispensable tools in astrophysics, providing the foundation for simulation of galaxy formation, star cluster evolution, and also the interstellar dynamics. Large-scale cosmological simulations rely on the mathematical modeling to replicate the revolution of the universe from its earliest stage to the present. N-body simulations, such as those pioneered by Springer, use advanced numerical techniques to model the gravitational interaction of billions of particles, successfully reproducing the formation of galaxies, dark matter halos, and cosmic filaments from primordial density flu- fluctuation. These simulations incorporate general relativity, fluid dynamics, and dark matter physics to predict the large-scale distribution of matter in the universe, offering insights in the galaxy clustering, cosmic wave formation, and also the role of dark energy. High performance computing and adaptive mesh refinement techniques enhance the resolution of these models, allowing scientists to explore structural formation across different cosmic epochs. The ability to simulate, analyze, and predict large-scale cosmic patterns highlights the immense power of mathematical modeling in astrophysics and providing a deeper understanding of the fundamental force shaping the universe. Fourier analysis is a fundamental mathematical tool in astronomy, enabling scientists to decompose complex astronomical signals into their constituent frequencies. This technique is particularly crucial for analyzing the light spectra from distant galaxies, allowing the astronomers to determine the chemical composition, temperature, and motion of celestial objects through the spectroscopy. By breaking down the starlight into its component wavelengths, Fourier's methods help detect the exoplanets via radial velocity shifts, measure the rotational dynamics of galaxies, and study the cosmic background radiation. Additionally, this analysis is essential in radio astronomy, where signals from pulsar and distant quasars proceed to reveal hidden astrophysical properties. In cosmology, Fourier transform aid in modeling the cosmic microwave background, providing insights into the early universe, dark matter distribution, and large-scale structure formation. Furthermore, the signal processing technique based on the Fourier analysis enhance gravitational wave detection by isolating the weak weak waveform barrier in noise. Applying the mathematical modeling and spectral analysis, astronomers can quantify cosmic phenomena, re, reconstruct celestial events, and refine our understanding of the universe evolution from the Big Bang to the formation of galaxies and star system. In conclusion, mathematics is indispensable in astronomy, providing the foundation for precise calculations, data analysis, and theoretical modeling, from predicting planetary motion by using the Newtonian mechanism to stimulating galactic evolution with numerical relativity and cosmological simulations. Mathematical tools allow scientists to decode the universe complexities. Techniques such as the Fourier analysis, machine learning, and statistical modeling enable the astronomers to analyze the vast dataset, detect the exoplanets, and also study the cosmic structures with unprecedented accuracy. Mathematics also play a crucial role in understanding gravitational waves, dark matters, and also the expansion of the universe, shaping modern astrophysics and cosmology. As technology and computational power continue to advance, the mathematical application in astronomy will be evolved further, enabling new breakthrough and pushing the boundaries of human knowledge about the cosmos. So that's all for me. Thank you very much.